Okay, Story, welcome aboard. We've got about a 6-minute video to show you here, and we'll bring you back on the flight deck for a little bit at the end of it. Here we are on the middeck, and I'll show you just a little bit of the assembly of the MBP, or multi-body platform, that is the main attraction of the MACE, or Middeck Active Control Experiment, that we ran on Endeavour here for the last 16 days almost. And here I'm assembling 2 of the struts and an electronic data connector to one of 3 nodes. The node in the middle has 3 rate gyro assemblies connected to it, as you can see there. I translated over to the ESM, or Experiment Support Module, which is housed in one of the lockers, and also includes the disk drive where the data is stored. And the data gets across on the white umbilical that you can see there. Also in the frame right now is the KISS box that we've been using all along for getting data to and from the ground. Is that blue box on the locker that you see. The MVP consists of 4 struts, 3 nodes, 3 rate gyros that are mounted orthogonally, and then at either end there is a 2-axis gimbal assembly, and the end behind my head there is the secondary or disturbance end. And the other end on the left of the screen is the primary end, or the end that we're trying to control. And the whole idea here is to put a disturbance end to the end that I have my hand on there that actually shakes the whole structure and will in fact disturb the performance of the primary end. And the idea is through active support or active control of the assembly on the left to actually allow that or enable that gimbal to point very accurately at a single point in space. And this would simulate a spacecraft that had, say, a scanning device at one end and a pointing device requiring great accuracy at the other end. Here we're starting a run that has a disturbance going in at the far end, and we'll be trying to control the left side here. And the control has just kicked in, and we'll give you a couple of close-up views and give you an idea of what this really looks like. And the vast majority of the runs that we ran were a lot like this. We'll show you a few that didn't work out like this too. This is the disturbance end, the secondary gimbal, and you can see that shaking the whole assembly. And in fact, at the primary end, which is not being driven, just being disturbed by the disturbance end, you can see it shaking here, and then the control will kick in right there, and you can see that it settles down very, very nicely. And while we were doing this, we were uplinking new controllers, downlinking the data, and the folks at MIT were looking at that, and they were writing better controllers, and the performance of these controllers got better and better as the flight went on. Here I'm mounting a laser pen to the primary end so that we can demonstrate for you just how remarkable this active control is of this device. Here the disturbance has gone in, and you can see the laser spot against the sleep station, and the control goes in right there and very accurately points the primary end. Now, not every single controller worked this way. Some of them performed, and like I said, the vast majority of them performed very well and got better as the flight went along. But there were some, like in this case, you can see the spot against the sleep station is being driven at a high frequency and is actually being driven off the target. And this is not the kind of control that you'd like to see. But it does demonstrate that if you're not careful, you can actually make the problem worse by designing a poor controller. And you can make it bad enough that it actually completely over-controls the structure, as you see here. We had several different configurations of the multi-body platform. Here's configuration 1, and it's actually the configuration that we ran the majority of our runs in. And this is another one of those controllers that did not perform as well as you'd like, but on the other hand, we were learning an awful lot from these controllers that went into these divergent states. And then the final configuration that we had was actually the most fun. It was configuration 2, the original configuration that we showed you, plus what we called flex appendages, which simulated, say, solar arrays on a space station or a spacecraft of some type. And you can see those at the orbiter's z-axis, along the orbiter's z-axis in the middeck. And here's another one of the controllers that actually drove the whole assembly into an over-control or out-of-control situation. And the amount of travel that this particular vehicle would have taken was actually limited by the tethers that you see there, or it would have gone flying on into the overhead of the lock face forward of the assembly. But you can see that if this was your space station, you'd be getting quite a wild ride. Well, those were actually the most fun to watch, but of course what we were trying to do was control the pointing end very accurately, and we wanted to close showing you again another protocol that had the same kind of excellent performance as the first one that we showed you. There are the disturbances in, and now the control. So we wanted to have a chance to talk to you about the Middeck Active Control Assembly. We had an awful lot of fun with it on orbit, but more importantly, we think that it's exactly the kind of human interactive experiment that we ought to be flying on the Space Shuttle. And the folks at NASA's Langley Research Center, at their Control Structures Technology Group, working with the folks at MIT, should be very proud of the experiment that they put on board. We think it's the kind of work that we ought to be doing. We had a lot of fun with it, and we hope they get to fly again. That's it from Endeavor.
Hey, Oz, thanks very much. That was really a neat summary, incredibly well put together. Video and audio are wonderful. We enjoyed coming on board and seeing that. It was a great explanation, too.
We had fun putting it together, Stuart. Glad you enjoyed it.
Yes, sir. It's what space is all about. Thank you.